on June 13th, Uniswap announced Uniswap version 4. While it hasn't been deployed to a production network just yet, the code is available on GitHub, and there are a lot of interesting things you can do with it. So with version 3 in 2021, Uniswap introduced concentrated liquidity. It was a very powerful but also a very opinionated approach to try to improve liquidity and how to handle liquidity on decentralized exchanges. But with all of those new features, gas fees was also pretty high compared to Uniswap version 2, but it allowed builders to create some great integrations. With version 4, they're now making it less opinionated and offering more choice to the users. So they introduced these things called hooks, which are essentially smart contracts that can hook into the lifecycle of a trading pool on Uniswap. So pools on V4 can choose to make their own trade-offs however they like. For example, accepting a higher gas cost in exchange for a feature set that is similar to V3, or add entirely new functionality. So with this new customizability that is possible, it is no longer necessary to fork Uniswap to create a derivative DEX, which was slightly modified version of Uniswap that makes the trade-offs you want to make. Previously, we've seen a lot of Uniswap forks get launched because of this exact purpose. But now with hooks, since you can plug in directly to the pool and run custom code at different parts of the pool's lifecycle, you can just deploy a pool with your custom hook and it will work alongside all the other pools in Uniswap version 4. There are a number of different hooks that are possible, but we're going to look at creating a project today that allows users to place take profit limit orders on Uniswap. So a take profit order is a type of limit order that very common on centralized exchanges that basically specifies the exact price at which a trader can close out their position for a profit. And that order is only filled if the asset reaches that limit price, otherwise it remains open. So for example, if ETH is trading for 1,000 DAI right now, I can put in a take profit order like sell all my ETH if ETH ever hits 1,500 DAI. And when the price increases, when 1 ETH is equal to 1,500 DAI, all my ETH will automatically be swapped into DAI. This is very common on centralized exchanges. But historically, Uniswap has worked more of like a market trader. You can buy and sell at the current market price. With hooks, since you can do basically anything you want, today we're going to see how to add the functionality to be able to create take profit limit orders on Uniswap version 4. So we're going to start off by setting up a new Foundry project. Yes, we are using Foundry this time. So make sure you have Foundry installed on your computer. If not, I'll have the link in the description on the installation guide of how you can get it set up. Once you have it set up, go to any directory and create a new folder in there. I'm going to name mine Uniswap v4 take profits. And then enter into this directory, and we'll set up a new Foundry project by running forge init dot. And you can see it would set up this basic structure for us that comes with a sample counter smart contract and the forge standard library installed and whatnot. Once we have this ready, we need to install the Uniswap v4 periphery code base that gives us the base hook contracts and stuff that we will be extending to create our own hooks. So we're going to type forge install and then github.com/uniswap/periphery-next. And this will basically clone that GitHub repo inside the lib folder. So we have access to all of those smart contracts and we can extend them however we want. If this is your first time using Foundry and you've previously only used Hardhat, in Hardhat, we'd be installing dependencies through NPM inside node modules. In Foundry, they get basically directly cloned from GitHub into your lib folder. And once this is done, another thing we need to do is set up our remappings. So again, if you're used to Hardhat, import smart contracts from your node modules folder. Now in Foundry, you have to import them from the lib folder. But if I go into counter.sol And writing code like import ERC20 from ... /lib / whatever, this doesn't look very nice, and it leads to having really long path names which don't look very nice. So Foundry comes with this thing called remappings that basically let you create an alias to the path you want to import. So Forge is smart enough that it actually already detects the folder paths that we may be interested in, and we can look at them by typing Forge remappings. So you can see it already detected the remappings based on the periphery next repo that we copied. So all we need to do is take all of these remappings and write them into a remappings.txt file. So it is recognized by Foundry when compiling our code and all of that. So we'll just do forge remappings and write to remappings.txt, and it will create this file. And you can see, for example, it has remapped over here periphery-next to lib/periphery-next/contracts. So if we need to import something from lib periphery next contracts, we can just do periphery-next/basehook.sol, for example. Great. With that done, let's take a minute to kind of understand how we are going to design this system. The goal is to have some sort of generic hook that allows users to place and cancel take profit orders on chain. Then at some point in time, somehow, we should be able to fulfill those orders if the price has changed enough to make that happen. And once an order is fulfilled, the user who placed that order should be able to claim the swapped tokens back into their wallet. On a high level, we have a few different functions: place order, cancel order, redeem tokens, and so on. So let's just start writing our code, and we'll go through sort of the explanation of how it works as we do it. So under src, I'm going to create a new file. We'll call it takeprofitshook.sol. And we'll set up a basic boilerplate over here. There we go. So let's go quickly through what this is doing. So, we specify the Solidity version. We import a few different base contracts that we will need to extend. So we have base hook, we have pool manager, and we have the hooks library. We also imported ERC1155. I'll come back to this in a second. And then we set up a basic sort of contract boilerplate where takes profit hooks is base hook, so it's extending base hook, and it's also an ERC1155 contract. And in the constructor, we simply initialize these two, and we have a function called getHooksCalls. Now, this is a required function that comes from the base hook contract, and it is essentially telling Uniswap which hooks are we going to implement. So as I said before, there's a variety of different hooks you can hook into, right? So for example, before initialize, this is a hook you can write that will be called before a new pool is set up. And then after initialize is kind of the hook that gets called after a new pool is set up. And similarly, we have like before swap, it gets run before a swap happens in the pool, and then after swap, and so on and so forth. In our case, we will be implementing two hooks. So we'll implement after initialize and we'll implement after swap. So these two are true, everything else is false. With this in mind, we can now start thinking about how this is all going to work. So I want to take a quick detour over here to understand something called ticks. So ticks in Uniswap are a term that you will see throughout the rest of this code, and it has a lot to do with how Uniswap version 3 and version 4 handle liquidity. So essentially, we know that Solidity cannot support floating point numbers, right? So you cannot have like fractional numbers in Solidity. But we need to represent token prices with precision. So ticks are essentially a way to represent token prices of a pair in Solidity and allow you to perform complex mathematical operations by letting us represent some fraction of price movements as integers. So if you have to think about ticks conceptually, think of them as the smallest amount possible by which the price of an asset can move up or down, right? So, for example, in TradFi, in stocks, certain assets can only move up or down in increments of 1 cent, while others can move in increments of 0.01 cents, while others can only move in increments of $1 at a time. So, a tick is the smallest amount possible by which the price of an asset can move up or down. And then what you can do is, with that knowledge, you can actually calculate the price of an asset at a given time, at a given tick, using a certain equation. So the price at tick I is actually equal to 1.0001 to the power of I, where I equals the tick at that point. For example, let's say we start off with a freshly created pool that has token A and token B, and initially they are perfectly one-to-one, right? They're traded perfectly one-to-one. The pool has tick equals 0, and token A and token B trade one-to-one. So price at tick 0 at I equals 0 is equal to 1.0001 to the power of 0, which is equal to 1, right? The price of token A in terms of token B is 1. And now somebody comes in, they do a swap, they sell some token B and buy some token A, which causes the price of token A to go up and the price of token B to go down. And in this case, what will happen is the tick will reduce, right? So the tick may go down to, let's say, -50. And then the price at I equals -50 is then equal to 1.001 to the power of -50. This is actually equal to 0.99501, yada, 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 right? So what does this mean? This means that one token A is now equal to this many token B, because the price of token A went up. It is not important to understand how and where this equation is coming from. It is only important to understand the meaning of what a tick is, which is it's the smallest amount possible by which the price of an asset can go up or down, and they're used as a way to, like, ticks are integers, but they can be used to calculate the price of an asset, which is a fractional value. So it's kind of a workaround to Solidity not being able to support floating point numbers. What happens in ticks, another thing that happens in ticks, is each tick is spaced periodically, right? So since it's the smallest amount possible, let's say that there is some stock in TradFi that can only move in increments of $1, right? So it can only move in increments of $1, so the only possible values for the ticks are like 1, 2, 3, 4. But then when somebody buys or sells that stock, it's not necessary that the price movement that happens will always happen exactly in terms of $1, right? It might be like half a tick increase or 0.6 tick increase. So what happens is if we end up with a tick like that, we round it to either go to like the lower tick or the higher tick, right? So if actual tick equals 0.6, for example, and ticks are spaced at intervals of 1, then we round the actual tick to either tick lower or tick upper, which is 0 and 1 respectively. In our case, we will be seeing the term tick lower a lot, and we'll be seeing the term ticks in general a lot. But this is some background context I want you to understand. So now that we understand ticks, let's go back to our code, and we can add a few more things over here. So what I'm going to do, I'm going to import a couple of libraries that we need. We're going to need pool ID library, which is this library provided by Uniswap that just represents like a unique ID for a pool. And so we import it from v4 core libraries poolid.sol, and we need to use this library on pool keys. So pool keys are a struct that uniquely represent a pool, and a pool ID is used to convert that struct into a unique single ID for the pool. We can actually look at it. So if we go into poolmanager.sol, we can look at the struct pool key. So this is a pool key, and if we look at the pool ID library, what it does is it takes the pool key and it ABI encodes, then hashes it into a pool ID, which is essentially a bytes 32 string. Great. So we're using pool ID library for pool key, and we're going to create a couple of mappings. So one of the mappings we're going to create is going to be from a pool ID to a tick lore, and we're going to use this to keep track of the last known tick lore, right? What was the previous tick lore price for this pool? Since we're designing the hook in a generic way that it can work with any pool, we're going to keep track of, like, for this pool, what was the last tick lore that we know about. And to represent the limit orders that are placed by users, we'll create a nested mapping. And what we'll do over here is, so essentially when a user is placing a limit order, first of all, that limit order must be for some specific pool, right? It's, for example, like the ETH/DAI pool or something like that. So it's for a specific pool, and then it's set to be executed at a specific tick, right? It might be like at tick 100, sell all my ETH. It happens at a specific tick inside a specific pool, and then we need to keep track of which direction is the swap for, right? Like, for example, in an ETH/DAI pool, do they want to sell ETH or do they want to sell DAI? So this is represented by the 0 for 1 boolean, which 0 for 1 means you want to swap token 0 for token 1, and a false value means you want to swap token 1 for token 0. And then lastly, how many tokens do they actually want to sell, right? What is the amount? So we have this nested mapping, which will represent all the take profit positions that have been placed by users in our hook. And with this, we can now start writing a couple of helper functions to interact with these things. So I'm going to go down, add some helper functions over here, and we'll create a utility for set tick lore last that simply updates our mapping. So we take the pool ID, we take the tick lore, and this can be a private function, and it just updates it in the mapping. And then we can have a function for get tick lore at a given actual tick and given a specific tick spacing, because different pools will have different tick spacing. So here, this Copilot code is wrong. Here, we need to calculate the actual, we need to calculate the tick lore given the actual tick, right? So what we can do is we calculate how many intervals there are between the two. So for example, let's say tick spacing is 10 and the actual tick is 12, then intervals will give us 12 over 10, which will give us 1 because this is solidity. And then we can return the number of intervals by tick spacing to get the lower tick. But actual tick can also be negative, right? Because price can go down. So it's possible, like if tick spacing is 10, but actual tick is negative 12, then negative 12 over 10 will give us -1. But the tick lower to that is actually -2. It's not -1. So we need to add a check over here where we're like, if actual tick is less than 0 and actual tick mod tick spacing is not equal to 0, then intervals minus, and then we return intervals into tick spacing to get the tick lore. Cool. And for our hooks, we can now create our first hook, that is the after initialize function. And this hook will basically, this will be a really simple hook that just sets the initial, This will be a really simple hook that just sets the initial tick lore for the pool. So when a pool is first created, initially, it'll usually start off at tick 0, but it could be something else. But initially when the pool is created, we'll just update our tick lore last, and we can use pool key, convert the pool key to an ID. This is where this library is being used. So we do key.toID, and then For the tick lure, we use get tick lure given the actual tick at that time. And then every hook also needs to return the function selector for that hook. This is something required for Uniswap v4. So since this is the after initialize hook, we need to return take profits hooks dot after initialize dot selector. So we need to return the function selector for this function. And with this done, now what else do we need? Now, we still need a way for users to place their orders. We still need a way for users to be able to cancel those orders, and we still need a way for those orders to actually be fulfilled. Let's start off thinking about how we're going to place orders. So this is also where the ERC 1155 stuff will come in. So when you're placing orders, right, think about it this way. When you place an order, it may or may not get fulfilled, right? Maybe the price goes to that point or maybe it doesn't. If it does go to that point, and if the tokens do get sold and swapped for the other token, the user should be then able to come in and redeem those tokens back, right? So we need some way of identifying who this user was who created this order. And, a simple solution is we just keep track of like message.sender and whatnot. But if we want to be a little bit more flexible over there, what we can do is we can mint them receipt tokens, right? And this is where the ERC 1155 thing comes in. What we're going to do is when they place an order, we're going to mint them ERC 1155 tokens, the semi-fungible tokens, which represent their order, which represent their position. And then what they can do is while the order is placed, they can trade part of those ERC 1155 tokens to somebody else. They can transfer it to another wallet. They can do whatever it wants. And then eventually, if the order is filled, they can just come back, give us those tokens. We'll burn those tokens and send them whatever amount of tokens they want to withdraw, right? So the 1155 tokens will kind of act as a receipt, and later on, they can return those tokens to us to get their swapped tokens back out, or just if they want to cancel their order as well. So we're going to assign these 1155 tokens some special token IDs, which helps us identify which order it's for. If we look at our mapping, right, I mentioned earlier, if we look at our mapping, an order can uniquely be identified given the combination of the pool ID, the tick at which they want to sell, and the 041 amount, the 041 trade direction. It's also possible multiple people actually place the exact same order, right? I could place an order saying, I want to sell all my ETH if it ever hits 2,000 DAI in this specific ETH DAI pool. Another person could have the exact same order, but you only have claim over the amount of tokens that the NFT says you do, right? That the 1155 token says you do. And that is kind of like your share of that take profit order. Anyway, so let's create the function to get a unique token ID. And we'll add like a public pure. So it takes in the exact same information, the key, which can be used to get the pool ID, tick lore, and 041. And we can use this, we'll encode all of this information, hash it, and convert it to a UN256. We can use this UN256 value as the token ID. So we're going to create a few more mappings to keep track of some additional state. And we're going to need 4 mappings actually. So I'm going to just copy paste these 4 and we'll go over them. So first, we need a mapping for token ID to Boolean that says, does a token ID already exist? i.e., does that take profit order already exist? Because again, this is every time you place an order, it's possible somebody else had the exact same order previously as well. So we can check using this mapping if an order at that token ID already exists. Then we have these 2 mappings. So we have token ID claimable, which points to how many swapped tokens are claimable for this order right now. That is, if an order was filled, how many swapped tokens are available to be redeemed by users who placed those orders. And total supply is kind of the opposite of that, which is if an order hasn't been filled yet, how many tokens do we have that still need to be sold, right? So for example, this could be how many ETH do we have that I still need to sell, and this is how many DAI do we have that is ready to be redeemed by users, right? And then token ID data is a mapping that goes from token ID to the original things that went into calculating the token ID. And this can having this information allows us to look into take profit positions if we need to in the future. Great. With this boilerplate setup, we can now start writing our place order function. We're going to import a couple more libraries. Also, I don't know why this happens in VS Code with me, but it's not actually an error. It's just some weird behavior. If I reload my VS Code, you'll see that it goes away. I don't know why. But anyway, we need to import a couple more libraries. So what we're going to do is I'm going to import these two. So we have currency library and an interface to ERC20 tokens. Now the second one is obvious. When people are placing orders, we need to transfer tokens from their wallet to our wallet and lock them up while the order is pending. So we need ERC20 interface to access that. And currency library is, so when Uniswap v4 identifies tokens that are part of a pool, part of a trading pair like ETH/DAI, it represents them as these things called currencies. But we're going to need to get their actual contract addresses to interact with those tokens using ERC20. So we need the currency library to do things like that. So we're going to start using that library. I'm going to type using currency library for currency. And now we can start writing our place order function. And I'll mark this under core utilities. So we have function place order. And this will take in the pool key, right? This will take in iPool manager dot pool key call data, pool key call data key in 24 tick at which they want to sell, into 56 amount in how many tokens they want to sell, and 0 from what direction do they want to sell in. And we'll make this return and in 24 the tick lower for that position. So first things first, we need to calculate the tick lower for this actual tick that they want to sell at. So we get the tick lower, and then we can place their order. You can be like take profit positions key.toID tick lower 0 for 1, and increase the amount of tokens in that order by however much amount they want to put in. And then we check, does this token ID already exist, right? Oops, I need to calculate the token ID first. So we calculate the token ID for the receipt tokens. And once we have that, we check, does this token ID already exist? And if it does not, then we mark it as existing equals true. And we set the token ID data for this to destruct. Once this is done, we can mint the receipt tokens to that user. So we'll mint them ERC loan 55 tokens with this token ID and an amount equal to how many token A they're trying to sell or token B they're trying to sell from this pool. And then we can increase the total supply we have available to be sold for this order by amount in. And then lastly, we need to transfer the tokens from their wallet into ours. So it will be address token to be sold contract. And depending on the direction, if it is a 0 for 1 swap, then this will be currency.unwrap pool key.currency0. So if they're swapping the first token to the second token, they're giving us token 0. So we get that address. But if it's a 1 for 0 swap, then we unwrap currency 1. And finally, we do ERC20 token to be sold contract, transfer from message.sender to our address and this amount worth of tokens. And then we can return them the tick lower that we used to place their order. Perfect. So if the price of their token ever crosses this tick lower, we need to sell their tokens and execute their order. Great. With place order now done, we can now do cancel order as well. It's not that much different. So we can write cancel order, and this takes in basically the same arguments, and this will also be an external function. And again, in this case, we calculate first the tick lower for the actual tick that they have specified. So tick and key dot tick spacing, and then we get the token ID for their order, and then we calculate how much balance do they have. And this balance, by the way, this balance of here is coming from ERC 1155. So we're essentially checking how many ERC 1155 tokens do they have for this token ID, and this must be equal to the amount of tokens they wish to sell that they originally put in the order, right? So, or sorry, not exactly equal, because they might only want to cancel part of that order. So originally I could have been like sell 10 ETH if ETH ever hits 2000 DAI, but later I changed my mind. I'm like, no, only sell like 5 ETH if ETH hits 2000. So they must have some balance, right? Amount in must be greater than 0. Otherwise they have nothing to cancel, no orders to cancel. And with that, we can then modify the take profit positions, reduce that by the amount in. We can reduce the total supply for this token ID by amount in. We can burn all of these. We can burn amount in worth of ERC 1155 tokens from the user, and we take the contract address of the token they wish to sell, and then we send it back to them. Perfect. And now the order has been canceled. Now let's start thinking about how we are going to fulfill these orders. We're going to take another detour here to understand another piece of terminology for Uniswap. They have this thing called square root price limit x96. And this is interesting. So previously, I told you that ticks are used to represent the intervals of price movement, right? And they can be used to calculate the price at a given tick using the equation I showed earlier. There's another parameter called the square root price limit x96 that is also used to keep track of prices. Again, since Solidity does not support floating point numbers, complex alternative approaches need to be taken to make precise calculations possible. So long story short, Uniswap uses something called the Q notation. And the Q notation, you can convert a number from its Q notation to its decimal value and vice versa by following a specific equation. So, for example, if you have some value v that is in decimal, you can convert v to Q notation by multiplying v with 2 to the power of k, where k is some constant. And k here depends on how big of a Q notation you want to use. So in this case, we say square root price limit x96. This x96 part of it defines what type of Q notation is being used, and the number after the x specifies the value of k. So if we want to convert v to Q notation with x96, then we multiply v by 2 to the power 96, right? They also have some other Q notation numbers they use elsewhere. They also have like x64 and x128 that are used in different places in the code base, but those are irrelevant to us. But by using this alternative approach, what happens is this value, the Q notation value of v, this is a really large number, right? Because they're multiplying by 2 to the power 96. This is a really large number, and rounding it to its closest integer loses very little precision compared to trying to store v by itself. So for example, imagine V represented the price of token A in terms of token B, right? And let's say one token A was equal to like 1.000234 token B. You can't store this in Solidity. And if you had to round this, it would round directly to 1, which makes their prices equal. But the prices are not equal. So what you can do is instead, you convert this value, this V value, to Q notation at x96. And this will get you like V into 2 to the power of 96. In this case, will get you a really large number, which equals to this, which equals to this. And now this is an integer. This has definitely been rounded a little bit over here. At this point, this is an integer value that can easily fit in Solidity within a uint160 data type, which is what Uniswap uses to store these values. And it's integer, they barely lose any precision. If at all, they're losing very little precision in the token price compared to just trying to store this number directly. Okay, so coming to the point, square root price x96 is the Q notation value for the square root of the price like right now, usually. And right now, how do we calculate that? How do we calculate price right now? We calculate it with the ticks equation earlier, where we take price I equals current tick, whatever that may be, and that is equal to 1.0001 to the power of the tick I, right? So square root price x96 then is equal to the square root of the price at tick equals I, whatever that may be, times 2 to the power 96. And this represents the price ratio between the two tokens. Now, going off of this, with this in mind, square root price limit x96 specifies a limit on the price ratio. It could be a lower limit, it could be an upper limit. But essentially what happens is when you're making a swap on Uniswap, you have to set a slippage percentage. Like how much price impact are you willing to handle, right? On the user side, on the front end, you'd be selecting a slippage percentage, something like 1% or 5% or 10%. But to the contract, that slippage value is like the exact value is calculated and then converted into Q notation, and it's called square root price limit x96, and it sends that to the contract, which tells the contract, okay, this is the max or this is the lowest I will accept square root price x96 to go before you just fail my transaction. Why did we just go off on this rant? Because once we start talking about fulfilling orders, we need to do swaps on Uniswap programmatically, which means we also need to provide these limits and set reasonable slippage percentages based on what might be acceptable to the people who are placing these orders. Okay, now coming back to our code, back to fulfilling these orders. So what should we set the price limit to actually? In our case, we're going to set the absolute minimum or the absolute maximum price limit depending on the direction of the swap to make sure that these orders are always executed regardless of how big of a price impact happens. In a production design, if you were to deploy something like this to mainnet, it might be useful to ask the user when they're placing the order how much slippage they're comfortable with, but that is out of the scope for this lesson, and in our case, we're just going to always execute the market order regardless of how big of a slippage it causes, right? So with that in mind, let's start off thinking about how we're going to fulfill orders. So first of all, we're going to import a couple of things from Uniswap again. We're going to import one library and one data type. So tickmath is a library that allows us to do, has some constants and allows us to do some calculations on ticks. And balance delta is a data type. It's a struct that it represents like the price quote when you're trying to do a swap. So we won't start off directly writing the fulfill order function. We'll start off by first creating a helper called handle swap. And what handle swap will do, it'll be like the helper function that actually executes the swap, and it does everything that it needs to. It actually executes the swap, and we'll just call handle swap when we find an order that is ready to be executed. So this will be external returns, and we'll return a balance delta from here. Perfect. So in handle swap now, what happens is we're assuming that we have some swap that is ready to be executed, and we just need to actually execute it. So what we're going to do is we're first going to get a quote from Uniswap on what is going to happen if we wish to execute this specific swap. And balance delta, let's open up balance delta. So if you look at the balance delta library, it essentially has two values, an amount 0 and an amount 1. So what it does is when we call the swap function, Uniswap will return us the delta changes in balance, right? So let's say you're swapping token 0 for token 1, you're increasing the balance of token 0 and you're decreasing the balance of token 1 with that swap. So balance delta over here will contain those exact amounts, where amount 0 represents the delta change in token 0 and amount 1 represents the delta change in token 1, right? So we get a quote from Uniswap, and Uniswap will tell us, okay, this is how much delta changes need to happen. And then we're now responsible to make those delta changes happen. So the swap could be in one of two directions, right? It could be a 0 for 1 swap, selling token 0 to buy token 1, or it could be a 1 for 0 swap, selling token 1 to buy token 0. Okay? In the case of a 0 for 1 swap, amount 0 will be increasing because we're increasing the balance of token 0. So as long as you didn't put amount like equals to 0. So we check that if delta.amount 0 is delta.amount 0 is greater than 0, so we owe Uniswap certain amount of token 0 tokens. So what we're going to do is we're going to use IRC20 and currency.unwrap key.currency0, which is this will give us the address of token 0, and we transfer to the pool manager, not to message sender. We transfer to the pool manager that amount of token 0 tokens, what it expects from us. And once we've done that transfer, we can let it know that, hey, we've done this, consider this part, consider the token 0 delta to be settled. And this will cause the Uniswap contract to check and make sure it has received the tokens, right? The other delta that is changing is delta 1, and that is going to be a negative delta, right? Because if we're going 0 for 1, we're swapping token 0 for token 1, we're increasing the balance of token 0, but we're decreasing the balance of token 1. So the delta over here is going to be a negative value. And if it is a negative value, we need to request the pool manager. We need to take from the pool manager some amount of currency 1, which is token 1. So we ask it, we do pool manager.take, give me this token to this address for this amount. And note here we did negative delta.amount1, so we flipped the sign, right? So Uniswap told us, okay, for example, we're going to lose, like the delta for amount 1 is like negative 10. So we tell pool manager, okay, send me 10 tokens, right? We need to flip the sign. We're like, okay, send me 10 tokens, and that is the equivalent of a negative 10 delta. So this is all for like the 0 for 1 swap. The other side is pretty much the exact same, where if it's a 1 for 0 swap, in that case, the amount 1 delta will be greater than 0, because amount 1 is where the balance will be increased in this case. So similar to that, we do a ERC20 transfer and we settle it, and then the delta for amount 0 will be negative in this case, and we take currency 0 from the pool manager. And once this is all done, we return delta to whoever called the handle swap function. And with this helper in place, we can now actually start with the fill order function. And in fill order, this is not a hook, right? This is just a normal function. So with fill order, just forget about the hook. Forget about trying to figure out when an order should be executed. Just think about, okay, there is an order that's ready to be executed, and fill order is the function that's going to actually do the whole shebang, do all the execution. It is not concerned with how it actually gets executed, like sort of when it actually gets executed. Like, this is not the function that is tracking price changes. That needs to happen in a hook. We'll do that in afterSwap, but this is the main function that afterSwap will call to actually execute orders when it finds something that is ready to be filled. So in fill order, similar arguments as all the other functions. We take the pool key, take 0 for 1 and the amount in. We prepare the swap parameters, and this is where square root price limit x96 comes in. So we prepare some swap parameters, and to remove this comment, and this is like the configuration for how we want the swap to go, right? To fill the order, we want to make a swap that has the 0 for when value based on whatever the order was, and we want to swap amount in worth of tokens. And for the price limit, I said we're not really going to have a price limit. We'll just set the maximum slippage that is possible. So if it is in the direction of 0 to 1, we're going to use the minimum square root ratio plus 1, right? Think about this. If you're swapping token 0 for token 1, you're increasing the supply of token 0 and decreasing the supply of token 1, right? So you're making token 1 more expensive. If token 1 is more expensive than token 0, what does this imply? This implies that one token 0 is going to be some amount less than one token 1, right? And what we're doing is we're setting the limit to be the minimum possible ratio. So we're like, okay, like set it to be a really low number. So no matter how much price impact you're causing, this should execute. On the flip side, if it is a 1-for-0 swap, then that means you're increasing the price of token 0. So then one token 0 will be some like large number of token 1, right? And in that case, we're setting the price limit to be the maximum possible price limit minus 1. So this is essentially the equivalent. This whole thing is essentially the equivalent of maximum slippage allowed, right? And then what we do is we need to call our handle swap function, and there's a very specific way of doing this. So we actually need to let the pool manager call it. So we need to acquire a lock on the pool manager. The way it works in Uniswap version 4 is, since there's a single contract that manages all the pools, we need to acquire a lock on a pool at some point. And then while we have a lock on it, we can do whatever actions we need to do. We can swap, we can settle, we can take, we can add liquidity, remove liquidity, modify liquidity positions. We can do whatever we want to. And then we release the lock, and then all of those actions sort of happen like together while the lock was acquired. So in handle swap, we already took care of like calling swap, calling settle, calling take. But to be able to do all of this in the first place, we need to get a lock on the pool. And to get a lock on the pool, we need to do pool manager dot lock, and we need to give it a callback. So we need to tell it, okay, once the lock is acquired, I want you to call this function for me, which will execute the rest of the things we need to do. So we will be executing this dot handle swap with the following parameters, with key and swap params, and this will return us a balance delta. Right? Does this make sense what we're doing? So abi.encode call, we're encoding this handle swap function call. We're calling basically this dot handle swap with key and swap params, and we're converting this into like raw ABI encoding. Then we're calling pool manager.lock, right? We're trying to acquire a lock on the pool manager, and once the lock has been acquired, the pool manager will then further execute the rest of the code that needs to be executed, which is running the handle swap function. And once the lock function is complete, since you can essentially run arbitrary code over here, everything happens in like raw ABI encoded stuff. So we send it a raw ABI encoded function call, and it returns us a raw ABI encoded response. In our case, our handle swap function is returning a balance delta. So pool manager.lock, once it runs this, it will return us balance delta in like ABI encoding. So overall, we're doing an ABI.decode on it to convert it to an actual balance delta struct. Anyway, so at this point, our swap has been done. And at this point, what we can now do is we can modify all of our positions and be like take profit positions, key take 0 for 1, reduce the amount because that amount has been now swapped. And we get the token ID for this order. We calculate how many tokens we received from the swap. So amount of tokens received from swap. And this depends on the order. So if it was a 0 for 1 order, if it was a 0 for 1 order, if we sold token 0 to get token 1, then the amount of token 1 we received is equal to the negative delta of amount 1, because delta.amount1 would be a negative number. So negative delta.amount 1 is the amount of tokens we got. And if it was a 1 for 0 order, then negative delta.amount 0 is the number of tokens we got. And now we can be like, okay, token ID claimable that are ready for this is we have some more tokens claimable now. And that is all. That now fills our order. With this now ready to go, we can actually write our hook now. And we are going to be filling orders inside the afterSwap hook. And I'll tell you why. So let me actually just copy over this function declaration here. And one thing to note is we'll mark this a pool manager only function. So only Uniswap can execute this, and random people cannot try to call afterSwap and trick us. But why do this in afterSwap? So what we're going to do, since we want these orders to sort of execute automatically when the price changes, right? When does a price change? The price of tokens in a DEX changes when a swap happens, right? When some random person sells or buys a token from a pool, it affects the price of the tokens in the pool. So what we can do is after every swap, right, as normal people are doing their normal swapping in the pool, after every swap, we can look at what is now the current price, right? What is the new tick of the token? Like, what is the new tick of the pool? And we can compare this new tick to the last known tick that we have, because we have a mapping. We have a mapping that stores the last known tick for this pool. So we look at the new tick, we compare it to the last tick, and we're like, okay, did the price go up or did the price go down? Right? Did the tick go up or did the tick go down? So if the tick went up, that means the price of token 0 has increased, right? So we can now search for any open orders we might have for selling token 0 between the last tick and the current tick. And if the tick went down, that means the price of token 1 has increased. So that we search for any orders we might have to sell token 1 between the current tick and the last tick, right? So we search for those orders. If there are any, then we simply call our fill order function for each of those positions, and then the order essentially gets automatically fulfilled as the price was updated. Does that make sense? Cool. So what we're going to do over here is, first of all, what was the last known tick lure for this pool, right? So we get the last known tick lure for this pool. Then we get what is the exact current tick in this pool. So this function actually returns a lot of values, so we're just going to leave empty commas. We only care about the second value here, which is current tick, but pool manager.get slot 0 key.toID to ID. This returns us, I think, like 6 values or something. We only care about the second one, so these are all unnamed empty commas in case you're wondering what this is. So we get what is the current tick, and then we calculate the current tick lower value for this, because this is like the actual tick price. But what is the last interval? What is the lower interval to this current tick? Okay, so we have these 3 values, and then we check for orders in the opposite direction of the swap, right? So if the normal person who was just there swapping, if they did a swap in the direction of 0 for 1, they effectively increased the price of token 1. So we need to be checking for orders in the 1 for 0 direction, right? We need to check for orders in the opposite direction of the swap that just happened. So bool swap 0 for 1, our 0 for 1 value needs to be the opposite of the swap that this person just made. And we'll create an int to keep track of how many tokens we need to sell, if any at all, right? So this initially is 0, and then if we have any tokens that we need to sell, we'll use this to sell it. So now we check. So if the last tick lower was less than the current tick lower, which means tick has increased, i.e. price of token 0 has increased, right? So if the tick has increased, then the price of token 0 has increased. So what we can do now is we run a loop, like 4 into 24 tick equals, starting from the last tick up until the current tick lower. Is there any orders, right? So swap amount in equals take profit positions, key take swap 0 for 1. Are there any pending orders at this tick? If there are, if swap amount in is greater than 0, we call fill order. If not, we increase tick by the tick spacing. Because orders can only be at exact intervals of the spacing, because we place orders on tick lowers. So they can always only be at the exact intervals. So if between last tick lower and current tick lower there are any positions that exist with an amount greater than 0 waiting to be sold, then we fill that order, right? And the opposite of this, else, if last tick lower is greater than current tick lower, then we can loop through 4 int 24, for int 24 tick equals last tick lower, and while current tick lower is less than tick, we can loop, and similarly again check for any swaps that may exist, execute those swaps, and then reduce the tick value to proceed this loop further. Once this is all done, once we have checked and executed any pending orders that might be ready to go, we now take note of the new tick lower, update our mapping, and then at the end, each hook needs to return the function selector. With this, 99% of our functionality is complete. The only last thing left to do now is have a redeem function so users can withdraw their swapped tokens if their order gets fulfilled, right? So for this, we're going to import another library, this time from Soulmate. So we're going to import the fixed point maths library from Solmate to have access to like this one math function that we need. And we're going to use this library over uint 256 values. And then going back down, I'll create the redeem function, and this is going to be just like a external function where the user tells us their token ID, how much amount they want to redeem, and where to send the money. So first of all, we make sure there is something to claim at all in this for this token ID, right? If there is something to claim, we check if they have the ERC1155 tokens. We check their balance of ERC1155 tokens for this token ID, and we ensure that they have enough tokens representing the amount that they want to withdraw. Great. If they do, we get the token data for this token ID, and we figure out the address of the tokens we need to send to them. So if they placed a 0 for 1 order and the swap was filled, we need to send them token 1, right? And if they placed a 1 for 0 order, we need to send them token 0. So we get the address of the contract that needs to be sent, and now we calculate how much amount do we need to send them. So I mentioned before that multiple people could have added tokens to the same order, right? So we need to calculate how much amount we need to send to them, because they only told us how much amount they originally put in. So the total supply, we have a mapping for token ID total supply. So the total supply is equal to the total amount of tokens that were part of this order to be sold. This includes their amount in, right? So the users share their percentage ownership over the tokens that needed to be sold was equal to amount in divided by the total supply in that order, right? So their ownership over the swapped tokens is the equivalent of their share in the input multiplied by how many total claimable tokens are available for this order, right? So this can be written as, amount to send equals amount in multiplied by total claimable by total supply. So we use the fixed point mathlib here to avoid any rounding errors, but this is basically exactly this equation. So amount to send equals amount in dot multiply divide down, which means multiply it and divide it and then round down if you need to. So amount in multiplied by token ID claimable divided by token ID total supply. Once we have these values, we can update these mappings. So reduce the amount of claimable, reduce the amount of total supply, and we can also burn their ERC20 tokens. They don't need it. ERC1155 tokens, they don't need it anymore. And finally, send them the amount of tokens to their destination address. With this, our contract is now fully complete, and all we have left to do now is test it. So let's make sure everything is good. Let's do a forge build over here. And this is giving me a bunch of errors. Okay, after initialize, oops, I forgot to mark it anything. So this needs to be an external override pool manager only returns bytes for forge. Perfect. So all our contract is fine. It's building. And now it's time to write tests for this and make sure everything works as expected. So under test, create a new file called takeprofitshook.t.sol. This is Foundry syntax for specifying a test file. It must end with t.sol. And here we're going to test 4 things. We will test that place order works, cancel order works, and we'll place an order in 0 for one direction and have it execute by performing swaps, and then the vice versa. We'll place an order for 0 direction and have it execute by performing other independent swaps. And the way Foundry tests work, we need to set up our testing environment to be able to do all of this, right? Since Uniswap isn't actually deployed on a network, and we're also going to be running these tests locally on our computer, we need to deploy 2 ERC20 tokens, that will be part of the pool. We need to deploy the pool manager contract. We need to create a new pool in the pool manager contract with these 2 tokens. And we need to add some initial liquidity to the pool. So this setup is required before we can even start running tests on our code. So in Foundry, this happens in a special function called setup in a test file, and we'll write this. But there's also another problem. There's one problem with this function called validate hook address. So I'll keep this short, but the way Uniswap v4 is designed, it requires that hook contracts follow a very specific contract address pattern. It requires that certain bits in the address itself are 0 or 1, depending on whether that hook implements certain functions or not. So when Uniswap is actually deployed to a network, this will likely happen through the use of counterfactual deployments using the create2 opcode. So hooks can be deployed to addresses that will pass the validation check. But in our case, that is not happening. And in our case, we need to somehow override this validate hook address function to make it work. But while we could have the override function directly in our hook, it's not a very elegant solution, because if we were to deploy it to an actual network and we accidentally forget to delete that function while deploying it, it's kind of bad. So we don't want to add that override in the main contract file, because that is just polluting the main contract file, and we need to constantly add it and remove it depending on, are we doing local testing or are we testing on a real network somewhere. So to solve for this problem, the Uniswap authors have a sort of hacky but clever solution for this, which takes advantage of some Foundry cheat codes. And cheat codes in Foundry basically let you do things in the testing environment that are impossible to do on a real network, such as like modifying and accessing contract storage or EVM storage directly. So the idea is we have our main contract, the one we just wrote, takeprofitshook.sol. What we're going to do is we are going to create a stub contract, and we'll call this takeprofitshookstub.sol, or just takeprofitstub.sol. And this takeprofitstub, it will inherit from our main contract, but override the validate hook address function. And then in our testing environment, we'll use cheat codes to overwrite the storage, i.e. the contract code and any other values in the main contract with our stub implementation. So this approach, it doesn't pollute our main contract, right? We don't have to have that override over there simply for the sake of being able to test it. It lives in a separate file, but in our testing environment, we can use the cheat codes to etch over the main contract and just override it with everything. So we'll quickly go and create our stub file. Go to src create takeprofitshookstub.sol, and this is a really simple contract. So all it really does, it imports the takeprofits hook. It declares a new contract that extends takeprofits hook and has the constructor for it. And the only other thing it does is override validate hook address and make it like an empty function. So nothing happens when this function gets called. Once this stub is there, we can now start setting up our testing environment. So I'm going to import a bunch of things that we will need. So we imported a couple of Foundry standard libraries, so the standard testing library and a gas snapshot library that tells us how much gas our functions are using. We import test ERC20 token implementation because we will be deploying a couple of tokens. We import all the libraries that we'll need, currency library, pool ID library, and so on. We import the interfaces we will need. We import pool manager, pool modify position, and pool swap, and we'll get to this, but these are basically the pool manager contracts we have to deploy to sort of simulate the behavior of Uniswap. And then we have our contracts, take profits hook and take profits stub. With this, we can start writing our state variables. So I have a few different things to keep track of over here as well. So we first of all, we start using the two libraries that we need. So our pool ID library and currency library. And then for our hook, we hard code the address for our hook instead of deploying it, because we will just simply overwrite the storage of this hard coded address with the stub code during setup. And then we keep track of the pool manager, the modify position router, and swap router. So these two are the test version of contracts that are given to us by Uniswap that allow us to like modify liquidity positions or execute swaps on V4 in the testing environment. Then we have two tokens that we will be deploying to create the pool. And then we keep track of the pool key and the pool ID. And lastly, this random number, square root ratio 1:1, this is the Q notation value. So remember, we're talking about Q notation. So initially, when we add liquidity to our pool in our testing environment, we're going to add equal amounts of liquidity for token 0 and token 1, effectively setting them to be a 1-to-1 price ratio. So this value is the Q notation for 1. It's literally like if you just do 1 times 2 to the power 96, which is the Q notation value for V, for 1, you get this number. So this is the Q notation value for 1. With all of these state variables set up, we can start writing some helper functions. So first, we'll create a helper function that deploys our two ERC20 tokens. So you can see it just takes token A, token B, creates new, deploys them, and then we assign token 0 and token 1. And the way these two are assigned in Uniswap is based on the address of those token contracts. So the one with the lower address is token 0, and the other one is token B. So each pool, like you can't have pools like ETH/DAI, but then also DAI/ETH, right? Because only one of them has a lower address than the other. So token 0 and token 1 are the same, even if there's multiple pools for the same two tokens available. And then we need to write our code to stub the validate hook address function. And this includes some Foundry cheat code. So I'll go over it a little bit, but don't need to worry about it too much. It's a one-off thing, and you can find it in sort of the Uniswap testing docs and how they did this. But essentially what we're doing is we deploy our stub contract. We fetch all the storage slot writes that were done during the deployment. So everything that was written to Ethereum storage when this contract was deployed. We then etch the code. We take the code at the stub address and we etch it onto our hook address instead. And remember that hook was hard-coded, like we just hard-coded an address for this. We didn't actually deploy it, but we're taking this code and we're etching it onto that address. So now that address has this code, and then we replay all the storage slot writes. So we go over all the storage writes that were done during the stub deployment, and we rewrite them onto the hook's address as well. So effectively, we deploy the stub, and then we take all of that and put it into this hook address for our testing environment. Then we can now create our pool. We can initialize our pool. So the initialize pool function, we deploy the modify position router, we deploy the swap router, and we specify the pool key and the pool ID for the new pool we want to create. Essentially, we want to create a new pool with token 0 and token 1 that has 3% fees. Tick spacing, we're going to choose tick spacing equals 60, so price goes up or down in intervals of 60 units. And then we're specifying our hook contract over here, and then we just call pool manager.initialize with initial square root price ratio equals 1. And once the pool has been initialized, last thing we need to do is add some liquidity on there. So for liquidity, we'll mint a bunch of tokens to ourselves, to our own address, and then we'll approve the modify position router to spend these tokens, and we'll add liquidity across different tick ranges. So we can do concentrated liquidity in version 4 as well. So we'll concentrate our liquidity across 3 different ranges. So we'll add 10 ETH, 10 to the power of 10 to the power of 18 amount of tokens from tick ranges -60 to +60, then another 10 from -120 to +120, and then 50 at the minimum possible to the maximum possible. So like no concentration like throughout the entire pool. And then we approve these tokens for swapping through the swap router. With all of these helper functions created and the boilerplate done, we can write our actual setup function, and this just deploys the ERC20 tokens, deploys the pool manager contract, stubs our hook address, initializes the pool, and adds liquidity to the pool. And actually, we need to do one last thing. We need to add support for accepting ERC1155 tokens. So if you're coming from Hard Hat world, in Hard Hat, when you're running tests, the signer, the address that's engaging with your contract in the testing environment, that is a EOA. It's an externally owned account, so you don't need to do anything special for it. But in Foundry, when you're running tests, as you've probably noticed by now, our test is the smart contract itself, right? We have a smart contract that is running these tests. And since smart contracts are not EOAs, they can't just magically have ERC1155 tokens sent to them. Therefore, we need to add a couple of constant functions that come from the ERC1155 standard, saying that it's safe to mint 1155 tokens to this contract because it understands them and can handle them. This was added in the 1155 standard to avoid accidentally minting 1155 tokens to a smart contract that doesn't know how to deal with them, causing them to be lost forever. So we just add these two on ERC1155 received and on ERC1155 batch received functions that are just sort of constant functions that just return this function selector. And this tells ERC1155 contracts that this contract can receive tokens from us, and it's fine. Okay. Perfect. Now let's write our actual tests, finally. The first test we'll do is we'll write test place order. And in Foundry, note that all your test functions must begin with test underscore. If you don't do this, it won't run this test. So in place order, we're just going to do a simple, we're just simply going to place an order and make sure everything works as expected. So what we're going to do, we're just going to say, okay, at tick 100, I want to sell 10 tokens in a 0 to 1 direction, 0 for 1 direction. And we can test this. What we're going to do, we calculate our original balance. How much token 0 do we initially have? We approve our hook address to spend these tokens, and then we place an order on our hook with these values. And then we calculate how much token 0 we have now after we place the order. And we should now have a lower balance, right, first of all. So we start asserting a couple of things. We first assert that tick lower is 60, as we set tick to 100, but our pools space out ticks at intervals of 60. So when 100 gets rounded to tick lower, the closest tick to it is 60. So our actual order was placed at tick equals 60. And we can assert that our original balance minus new balance is amount. So amount worth of tokens have been transferred to the hook. Then we check if we received the 1155 received tokens. So we get the token ID for our order, and we check the balance of our address for this token ID, and we assert that this token ID exists and that we have equal number of 1155 tokens as the amount of tokens we put in to the order, right? So let's type force test, and this should pass. Oops, setup failed. Intake profit hooks.t.sol, EVM error word in setup somewhere. Okay, something is wrong with our setup. So what are we doing here? Okay, so in our setup, it was deploying all of these things, initialize, validate, all of that. That seems okay to me. Let me reload VS Code so I can get proper errors quickly, in case I'm just missing something there. Okay, so this all actually looks fine to me. I'm just going to run forged test with high verbosity once to check exactly what is going wrong. And oh, FFI disabled. Yes, I forgot. So since our tests are calling external contracts, in our case, we're calling the pool manager contract, we're calling our hook contract, and so on, we need to enable this thing called FFI in Foundry. So to do that, you simply go to your foundry.toml config file and just write FFI equals true. And now if I run force test again, you'll see test place order passed. And this is the counter test for their sample. I'm just going to delete this file so it doesn't show up when we're running tests. So we'll just do force test again. One test passed. Perfect. So with place order now working, we can now start writing our second test. Cancel order. This is going to be fairly similar. In this case as well, we simply we place an order. So the first half of the code is basically the same. We set these values, original balance, place order, check new balance, assert that tokens got transferred, and check that we received ERC1155 tokens. So far, so good. The only additional thing here is then we go ahead and we cancel the order on the hook. And after canceling that order, we check that we've received our token 0 tokens back and that all ERC1155 tokens have been burnt. So our final balance of token 0 must be equal to original balance, and our ERC1155 token balance for this token ID is 0. Great. Very basic tests, nothing too complicated. Now let's do a test for an order execution, and this one's a little more fun. This is where we see our code actually working. So we'll test for execution in the 0 for 1 direction. So we'll place a limit order for 0 for 1, and then we'll execute a swap separate from the order from 1 for 0, which will cause the price movement to, which will cause the price of token 0 to go up, and should execute the limit order that we placed. Okay, so here's that code. What we're going to do, so again, initially, the initial code is the same. So we set these parameters. We place an order to sell 10 tokens when tick equals 100. And then after placing the order, we do a swap separate from the order entirely. So we do a separate swap for 1 token in the 1 for 0 direction, in the opposite direction of our order. And we do the swap, and after the swap is done, we check that the order has been executed. So our take profit positions mapping should no longer have an amount for this order. The amount should be 0. And then we check that the hook contract has token 1 tokens ready to be redeemed, right? So we must have some claimable tokens for this token ID for our receipt tokens. And the hook contract must have a balance of token 1. That previously didn't, because we only sent it token 0. And since we're the only person who placed the order, all claimable tokens for our order is basically the entire balance of the hook contract. And then we will try to redeem these tokens, and we check our original token 1 balance, then we redeem it, we check our new token 1 balance, and this must be equal to claimable tokens, right? So I'll run force test again. And perfect, everything passes. And then kind of the opposite test of this, we'll do a test in the 1 for 0 direction very similar, except this time we're betting for a negative tick. So this time we're placing an order at a negative 100 tick, right? Because we want a 140. So when 140 happens, tick goes down. So we set an order at tick negative 100. We place our order. We do a swap in the opposite direction. So this time we do a swap in the 0 for 1 direction. And the rest of the code is pretty much the same. We execute the swap. We check that there are no more tokens left to sell. We check that our hook has token 0 tokens ready to be claimed. And then we redeem those tokens and check we got the right amount. Perfect. So we do forge test again. And the run successful. Awesome. And with that, you've completed this lesson. You've learned about Uniswap V4. We went from sort of not really knowing about V4 to creating our own limit order hooks on Uniswap. And you also learned about Foundry if you're new to Foundry here. So I think really great learning experience. This was obviously a longer video. I'm sure some of you have doubts, you have questions. So hop into the Learn Web3 Discord and somebody will be there to help you out if you have any questions at all. But for those of you who made it so far, everything's working. Great job to you guys. That's awesome. And if you enjoyed this, please let me know, leave a comment, like the video, subscribe, and let me know what you want to see next. And with that, thank you. Have a great rest of your day, and I shall see you soon.